here's a list of some petrology resources. I hope these are in your book. These two right here are interactive digital products. They're programmed in a way that you can click on stuff and it tells you what they are. So they're kind of fun. These two are free downloads. If you just Google smear slide, you can get these from the IODP. They're modern muds, and these are atlases of components in modern muds. So that might be of interest. Any questions?
Yeah, I have a question. You said detrital quartz almost never dissolves. What else never dissolves, like zircons?
Okay, so the question was, is there anything else besides quartz that's immutable, something that always survives for a long time? And zircon, certainly. Monazite, certainly. There may be some other, xenotime, something like that. Is a yttrium phosphate related to monazite? On the other hand, when it comes to phosphate minerals, we also see them as orthogenic precipitates. So it gets complicated. But there aren't many things that are so stable that they hang around for a long, long time. Well, I think if there is, and it relates to what I alluded to when I was talking about the wavelength of light, that the physics and the chemistry that apply to what's happening in a pore that's 4 nanometers across are not the same as the chemistry and physics that apply at a bigger scale. And people are just beginning to really start to look into that. But for example, there's a question as to whether cements can even precipitate in a pore that little, because the space that's available for the crystal may be smaller than the critical nucleation size. You have to have crystals of a certain size so that their surface area doesn't have so much energy that they just go back into solution. So you have to achieve a certain critical nucleation size. Well, if the pore is fundamentally too small for that to happen, that would put a fundamental limitation on the ability to put cements into those pores. So, there are a lot of questions, but there are some very good reasons to believe that chemistry and physics do not play out entirely the same at this really tiny scale.
Comment on the role of having quite a lot of organic acids in the associated environment.
So the question is, what's the role of organic matter in this overall reactivity? I think not all, but a lot of organic matter is really reactive. It's one of those components that if you have a bunch of it, your chemistry is going to really be affected by that. And the kinds of reactions that may go on in your rock are going to be really, at least over certain ranges of the burial history, are really going to be controlled by that. So it's really important. Oh, it's horrible. The question is, we have definitions for clay that has both a particle size, there's a clay size particle, and it's also a group of minerals. And it's terrible that this has happened, that our terminology has evolved this way, but you need to be keenly aware of it. That when you read a paper and somebody goes on talking about clay, you immediately need to go, whoa, which clay are you talking about? And here's another terrible thing, that in the clay size particles, different fields of study use different definitions. If you're a clay mineralogist, they often centrifuge out the less than 1 micron fraction, and to them that's clay. Other people use 2 microns, and the engineering literature generally uses 4 microns. So when you are reading papers, you really need to pay some attention to how they're defining these terms. And not all clay size particles are clay minerals. There's lots of clay size quartz, clay size feldspar, clay size heavy minerals, and in mud rocks. And Just because it's clay size doesn't mean it's a clay mineral. And some clay minerals also make big crystals. So orthogenic kaolinite is often in the fine silt size of the size distribution. So it's complicated.